Hi, I thought I'd do a video on LCR meters. What actually happened is that I received a new one and I wanted to do a video on that, but then I thought, well, I might as well explain that a little bit and discuss how we use these things and what other devices I have or that commonly are available to measure reactances for inductors and capacitors and so on. I started doing a video and then I realized that I myself had forgotten some of the principles behind AC circuits that I studied, when I was going to college like 40 years ago or something. So I had to refresh my memory on it. And then I thought, well, I might as well expand it and look at some of the other devices that we have that can measure these components. And when you first get these things, if you're not up to date with the AC circuitry and so on, they can be quite confusing. For instance, here I have connected a tiny little inductor over here, and it is marked to be 1 millihenry or 1,000 microhenries, and indeed, as you can see, 1.0296 is what it says it is. But these LCR meters, they have a bunch of features, and it may not be all that clear on the video, I'm not sure, but here is for instance a serial parallel button. If I select parallel, then suddenly the thing has doubled. It now says 2.1439 or whatever it is millihenries. The X, that means the reactance hasn't changed. So what the hey, what's going on? That's why I thought, well, let's discuss some of these things and what features you should be using and so on. But before we do that, we can have a quick look at this LCR meter and what features that it does have. Let's put this thing in auto mode. Now this is a very small inductor, and as you can see, when I put it in auto mode, it is measuring the resistance of it, which is very close to what the reactance of it is. You have to actually go to the inductance mode in order to see the inductance of it. But in any case, this thing has a button for level, and you can see the level on the screen here. Let me bring in the other camera so that you can see it a little bit better. There are some settings here that you can choose from the level. You can have 1 volt, 1.5 volts, 2 volts, and 100 millivolts. You have to be careful here because at 2 volts, some of the components, they might be overloaded or something. They might overheat or something. So you've got to keep that in mind as the appropriate voltage to test them on. I'm setting it to 600 millivolts right now. We have a frequency button here. It has a number of frequencies. It starts, this particular model has steps. It has like 16 different frequencies you can select from. There's a more expensive one that you can actually make it go up 1 hertz at a time, from 100 to 100 kilohertz. I did not need that feature, so I bought, it wasn't worth an extra $30 or whatever it was, so I bought this one. You can use these buttons over here, 120 hertz, 200 hertz, 400 hertz, 800 hertz, 1 kilohertz, and 2 kilohertz, 4 kilohertz. And do you notice that this value Q at the bottom is changing depending on the frequency? And there's other parameters as well that will be changing, because inductors and capacitors, the reactance of these components changes depending on frequency, so you need to know the frequency of the circuitry that you're going to use it at and select an appropriate frequency. As a rule of thumb, electrolytic capacitors should be done at low frequency, and other components, especially small inductors, they should be tested at a higher frequency. So their reactance is larger, and the machine will be able to more accurately show the value. In any case, that's what that's all about. Range here is not something that we need to worry about here, that is used when these benchtop LCR meters have provisions for testing a bunch of components. Like it says, you can create a list here, for instance, comparison. So you can actually say, okay, I received a bin of capacitors or inductors, and I want to make sure that they're all in range of, let's say, 5%, which is what that tolerance button here is for, of a particular value. Then you can measure the first one. You'll set the range to lock so that it stays in that range, and then you can just one after the other put the components in, and if one of them is out of range, it'll beep and it'll tell you so, or it can just record all the values in a list, and then you can look at them later on to see what the variances were. We're not going to be demonstrating that here. It's just a feature that these things have, and that's all we will save for it for now. What else is there? Speed. You can tell it to update the screen. Right now the speed says slow. You can make it update fast or medium. I always have it set to slow, but if you've got, as you can see, some of the digits, there is a little bit of noise or so on that it picks up, and some of the digits can be changing a little bit. Where the high speed might come in handy is you can actually select here some max, min, and average. You can select the average, and then if it is changing widely, then you can set it to high speed, let it run for a while, and then you'll know what the average value of that component is. It can show max and it can show min. There's not much difference between the 185 and 186. So it's kind of like pretty stable. Here is also a this set button brings up a little menu where you can change the language and the brightness, and there's a few other features there that you can set. Trigger source internal. There is it has a feature that there is a USB port on the back, and apparently you can hook it up to LabVIEW via an API called Skippy, SCPI or whatever it is, and in that case you can control some of these values. You can control this from a computer and make it do automated tests and things, I guess. Again, I'm not going to be using that, so it is of no consequence for our discussion here. Calibrate. There's LCR meters, they tend to have a calibrate issue, which brings us to how these things work. The benchtop accurate LCR meters, like the benchtop LCR meters like this one, they tend to have a accuracy of 0.01%. These handheld ones here, they have less digits and they tend to have a accuracy of 0.1%. So the benchtop one is 10% better, and these ones here, they just come with ordinary little leads with crocodile clips. Now they make them short for a good reason, because to avoid having too much, and you can plug other probes into it, so that the stray capacitors and inductance of the longer leads doesn't have a bearing on the readings. However, that is inconvenient, so they have found a way with these ones to make it possible to have longer leads. And roughly how that works is that there are 4 connectors here, and they tend to be shielded, but the shields are not connected to these Kelvin clips. They are internally connected to it's like an H-type circuit that shields it from some interference. And one of those, like this one here, is marked H-force and H-sense, and same with this one. So what they tend to do is there is these Kelvin clips. One of those is connected to like one of the side of the tips, and the other one tends to be connected to the other side of the tips. And then when you grab something with it, of course they become, they connect together like that. There's current flow, through both of them. So what actually happens is one of those is a low impedance output current source, and the other one is actually a very high impedance voltage measurement source, if you like. And those two then, because they're connected right at the tips here, that negates the most of the capacitance and resistance and what have you of the leads, and the same goes for the other one, both the same. So it's kind of a clever way to get them to be accurate. Now, all of these things have like a calibrate feature, like a shorted and an open calibrate feature. Let's get rid of these things. So you can hold down calibrate, and it recognized that the probes are shorted, so it's going to take like a count of 20, and it's going to be monitoring what it is reading on those probes, and then it knows whatever it is reading, it'll average that out, and then it will subtract that from the readings when you connect components to it. You can also do a calibrate with them disconnected, and that then measures, what the open connection interference or whatever it is that it might pick up, and it can equate for that as well. So I'll just let that count down. And meanwhile, so there's a button here to go to serial and parallel mode. I wish this camera was a little bit clearer. This is that I'm waiting for a better camera to come, but it hasn't arrived yet. But this one says auto, serial, parallel, so it'll cycle between auto, serial and parallel. See, that's a short OK. So here is reactance X, D for dissipation factor, Q for quality factor, and Q is actually the inverse of the dissipation factor, and theta, which is the phase angle, and ESR. We're going to be discussing those things. The mode of it can be in auto. Right now it is in auto mode, as you can see. When it is in auto mode, these buttons don't tend to do anything. but it's because it takes control of that. And as far as it is concerned, if you connect a let's connect a capacitor. If it is in auto mode, most of the time it might make the right decision. It's going to serial mode, and it is measuring 988.7 nanofarads, and it thinks that I want to know the dissipation factor, which in actual fact I'm not that interested in. So if you want to see some other values there, you'll have to take it out of auto mode and connect and manually select capacitance, inductance, or impedance. We will look at that. And as I said, the rest of the some of the other buttons here, like compare, you can compare different values. As I said earlier, you can set the tolerances to compare. You can let it fill up a list, and then you can save that and look at it again later on, and so on. As I said, we're not going to go into those details. You've already seen what min, max, and average does. It displays it on the bottom of the screen here, and which sometimes, if you're doing measurements that might vary, might be glitchy or something, then you can find out what the minimum and maximum was. This will also discuss DCR, DC resistance. For instance, if you want to know what the resistance of a inductor is without the AC component, in other words, it will just measure the resistance like a multimeter does with DC. You can push that button. If you are measuring this as a capacitor, this is specifically for electrolytic capacitors, or in fact other components that need a bias. And if you turn that on, you will see that the bias voltage here, it normally is 0 millivolts, so it's pure AC. But if you push the button here, it goes to ECA mode, and it now has a bias of 1.5 volts, and I set the level to 1 volt. The ones that are blue you can't change, the ones that are white you can change, and which allows you to hook up a electrolytic capacitor like this one. And this is actually a bad electrolytic capacitor, a known bad one. It is marked at 1500 microfarads at 6.3 volts, but as you can see, it has 662 microfarads, and in fact it varies. Sometimes when you hook it up, it'll be less. It has a very high and we got it sets to 220 hertz, which is appropriate for those electrolytic capacitors. So now if I hit ESR, you'll see that the ESR is 3.0391 ohms, and if you look it up on one of those little tables, for 1000 microfarads at the maximum should be 0.12, and it's a little bit more, so let's say 0.15, and it is 3 ohms, so this is a bad capacitor. It is not a good, you wouldn't want to use this. I pulled this out of a circuit where it had failed, so I know it's a bad one. So that's that is that. Anything else to say about this thing? I think that's about it, right? Yeah, I think I've got there's a hold button there that you can use in order to stop the display. See, it's flashing on hold now. you can actually measure a component, and then you can put it on hold and remove the component, and then you can still read it. Push it again, it's off. And the only other thing is this null button here. It just on most other meters that is marked as ref. So if you push that, if you take a little component, let's have a look at what a small capacitor here. And you hit null, see it goes into reference mode. This thing is, it's varying a little bit, but the idea is that you can put another component in place there, and it'll then tell you the variance between the two, whether it's greater or larger. Sometimes that can be handy. Turn that off. Okay, so here we have a small AC circuit connected, and just to show on the oscilloscope there how the signals can get out of phase with each other in AC circuits due to capacitors and inductors. It's a simple circuit. We have a capacitor and a resistor in series, and we have a little transformer here that is returning about 21 volts. And this yellow probe here, which corresponds to the yellow signal on the oscilloscope, is connected across the transformer, and then we have the purple probe connected around the resistor there. So when we can see, because the traces on the oscilloscope go from left to right, we see that the yellow trace is leading the purple one. So keep this in mind when we look at the results. When we measure the if you measure this circuit on an LCR meter, you will see that we will be presented with different values: impedance, phase angle, the resistive component, and the reactive components. And those four values will make more sense if you keep this in mind, as you can see that there are phase differences result from reactive components such as capacitors and inductors. Okay, just a little recap here of some of the parameters and values that you'll come across on an LCR meter. They are all related to AC circuits and reactive components such as inductors and capacitors. You saw on the oscilloscope that the voltage across the capacitor and the input voltage to the circuit are out of phase, and that can be shown by this little graph over here. We see that the RS, the series resistance, and that's what it will be called on the LCR meter, is on the horizontal plane here, and the reactance of the component will be on the vertical axis. It can actually be above or below depending on whether it's capacitive or inductive. In this case here, the example shows a 45-degree angle here, and when you blend those two together with that formula that you'll see up here or up here, you end up with a value which we call the impedance, and that's usually shown to be Z or Z. The actual reactance of the components is calculated with these values over here. 2 pi frequency times inductance, and 1 over 2 pi frequency and capacitance. And the capacitance, of course, is in farads, inductors in henries, and impedances in ohms, and all that kind of stuff, as you can see here. Okay, so anyone that has been exposed to AC electronics circuits and studied them in school would have come across complex numbers. And we looked at this little graph before. This particular graph here, the series resistance value would be the real number, and the reactive reactance would be on the vertical axis here, and that becomes the, as it says, the imaginary number. This is related to trigonometry and mathematical concepts, and which brings us to discuss it over here: rectangular versus polar coordinates. What it actually refers to is that you can record the value of a reactive component such as a capacitor and inductor in two different ways. There is a rectangular form, and there's an example given over here, 4 plus J3. In various parts of mathematics, sometimes they use an I in different branches of mathematics, but in electronics we usually use a J to notate that the value following it is the actual imaginary number. I believe J actually means the square root of -1, but I'm not a mathematical person, so I only know how to use these things in a practical way. So the 4 would be the series resistance, and the 3 would be the reactance. In that case it's positive, so it would have to be an inductor as well. Then if you want to get the actual impedance, you would use the Pythagorean theorem, which is you will take, as shown over here, you would take the square of 4 and the square of 3, and then you take the square root of it, which would then give you the actual so-called polar magnitude, which in our case would be the impedance. And if you calculate that out, it would actually be 5 in this example. To get the angle, you would take the arctan of the two numbers, and you would then end up with a value of the phase angle, how much it would be out of phase. And again, they can be positive or negative depending on the type of component that you are, capacitive or inductor, that you're dealing with. Okay, so that is how it works. Now, why would you use rectangular and polar form? You will find that the rectangular version is easiest to use to add or subtract the values of the components. And if you're analyzing a circuit, you might find that there is a capacitor and an inductor in parallel, or they are in series, or whatever it is, and it would be very similar to Ohm's law, the relationships of the components, but of course their values are not simple numbers, they are complex numbers. So the rectangular version allows you to, there's an example over here, you can add them or you can subtract them very easily, and you end up with a new rectangular complex number. Sometimes you need to multiply or divide them. In that case, you can still do it in rectangular format, but it becomes tricky. There's all sorts of rules and things. It's much easier to convert it to the polar form, and then you can just multiply or divide the impedances, and you can then, if you're multiplying, you can add the phase angles, and if you are dividing, you can subtract the phase angles. So that's how that comes about, and that is why there are for each component you can actually measure 4 distinct values on the LCR meter. There is the series resistance, there is the impedance, there is the reactance, and there is the phase angle. And the series resistance and the reactance put together would become the rectangular form, and the impedance, the Z or Z value, and the phase angle, the two together would become the polar form. And most calculators nowadays, scientific calculators, they have polar to rectangular and rectangular to polar conversions that you can also use to convert one to the other, which can be handy if you're doing calculations and so on analyzing a circuit. Okay, so the LCR meters can be operated in 2 different modes: serial resistance model mode or parallel resistance model mode. And it can sometimes be a little bit difficult to determine which model to use, but usually for most components actually you all go serial. But there is a rough guideline here. It varies if you listen to different manufacturers. Some quote 10 ohms, others quote 100 ohms. I think 100 ohms is probably more appropriate. If the impedance or the reactance of a component is less than or equal to 100 ohms, and this would be true for a small inductor or large capacitors, then use the series model. If you calculate the impedance or the reactance of the component to be larger than or equal to 10k ohms, this would be true for a large inductor or a small capacitor, then you would use parallel mode. Now for values in between, either one usually can be used, and there should probably be little variance between the two, but sometimes there could be some variation, and then you can apply these rules kind of thing to select the right mode. There's a little graph over here that is supposed to help you to determine to use the series model or the parallel model. As you can see, there is some frequency included here as well, and there is the capacitance or the inductance quoted over here. When it comes to frequency, usually depends on the component you're testing. For capacitors like electrolytic capacitors, you would usually use the 100 or 120 hertz, because usually they are used for filtering in power supplies and so on. If not, you can apply a little bit more frequency. For some electrolytics might be used in audio circuits, but the thing is that electrolytic capacitors are not meant to be used at a high frequency, so usually you will use them at a lower frequency, and often they are larger, so that you would be in series mode anyway. That's easy enough to determine. But if you've got smaller components, like very tiny capacitors, you can test those at high frequencies, and you may then well switch them to parallel mode, because they will have a high reactance or impedance value. So this little graph here gives you a little bit of a feeling for that. Okay, I've got it connected, that little inductor connected again. As I said, you can see from the screen here that it is set for inductance, serial mode, and reactance, and this is the reactance of that at 15 kilohertz right now it is set to. So this particular little inductor would behave and have that reactance 95 ohms and 1 millihenry or 1,000 microhenries. And as I showed before, so this is under 100, so you would want to use the series model, and indeed if I go to parallel, well, in actual fact it is so close to 100 it's not making much difference. What if we change the frequency here? You see how the frequency makes a big difference. At 15 kilohertz it was close to 100, and at that rate it didn't make much difference if you put it in a serial or parallel mode. But if you're measuring at 1 kilohertz, it is only 6 ohms, and it is way below the 100 ohms or so, and we really need to be in serial mode. And if I put it in parallel mode, it's just coming back with an invalid value. In any case, that is according to this rule here. If it is less than 100 ohms, and that's just a rough estimate, but it's 10 ohms for sure. You know, a very small reactance, a small inductors, you definitely want to be in serial mode. And if it is 10 kilo ohms or more, like for large inductors or small capacitors, you need to be in parallel mode to get an accurate reading, because the fact that, as I showed earlier, that the reactance doesn't change, but the inductance seems to change in that like before between serial and parallel, which tells you that it is actually a calculated value, and when it does the parallel mode model versus the serial model, it uses a different calculation, and that calculation can come back with a different value. So that is what you learn from that is how it works. Okay, so to get back here, so for a small inductor, large capacitors, with a reactance or an impedance of less than 100 ohms, use series model. If it is larger than 10k ohm, use parallel mode for sure. Values in between, you may use either one. Let's go to discuss how these LCR meters work compared to a digital multimeter. An LCR meter has a bridge circuit in it, Wheatstone bridge or whatever they call that. The component to test, device under test, DUT, is over here. Then it can adjust the impedance or resistances or whatever you want to call it on the other arms, and then there is different settings that you can use. It can be measuring capacitors with resistance in series. It can measure capacitance or an inductor, you know, with the resistance in parallel, and depending on all the values here, there's either going to be some current in either direction or none in the detection circuit here. And this thing is driven by an oscillator, and that is where the frequency thing comes in. Now you've seen me select, you know, 120 hertz, 1 kilohertz, 15 kilohertz, and what have you. That's the oscillator here. So what that means is that when you are testing a component, it is applying like a sine wave to it from an oscillator at a set frequency, and then it can actually measure the the current that is going to be flowing through these arms of that bridge circuit, and knowing what the other settings are on the other arms here, it can then calculate the impedance of the actual device, and it can also calculate the in a similar way like we showed on the oscilloscope, it can calculate the trailing or lagging of the voltage and current and so on, and come up with the phase angle. And the values, of course, that we want to know, like in henries and farads and ohms and so on, it can measure some of those directly, and others it can calculate and display. So there's also, of course, a as I said, DC resistance mode, which then actually uses not the oscillator but a DC voltage to measure the resistance, a similar way to a digital multimeter does. And multimeters, they actually work on a different principle. They don't have a bridge in them at all. If you connect a capacitor to a multimeter, it actually measures the current. It applies a voltage and it measures the current over time, and when the current goes down to zero or close to it, then it knows that the device, if it's a capacitor for instance, is fully charged, and then it can calculate the actual quantity of charge that has been transferred from that. This is usually a value in coulombs, and from that you can then calculate the capacitance, and then it displays it, and you will see that in action. Let's bring in the display of the LCR meter, and bring in the multimeter display, and we will hook up a capacitor. Let's have a look what we have. This is a it is particularly pronounced with larger capacitors. This is a 3300 microfarad capacitor. So let's do it on here instead of to capacitance. And this is an electrolytic, so in actual fact let's set it to proper electrolytic mode. And you see it immediately came up with, within a second, came up with 3223 something millifarads, 3236 microfarads, which is what that thing is, and it's got a good ESI, as you can see, 0.08, which is well within range, so this is a good capacitor. But now let's hook it up to the multimeter and see the difference. Let's give me a second here. There we go. Now this multimeter is that little O-on multimeter that I've got, and it is notoriously slow, but it demonstrates the features I'm talking about. It is actually, what it is doing is it is measuring the amount of current that this thing is absorbing, and I think it's the voltage that it's supplying might be a bit low or something, and it just takes, for a big capacitor like that, it just takes forever until, and it's auto ranging as well. It says overload for a while, and then finally it's narrowing down, so it's got its 3 3461, so it's a little bit less accurate as well, because I believe that the LCR meter here is more correct. You see how long that took? That is because it's applying a DC voltage to it, and it is just measuring the current going into that thing and calculating. Once it gets to a steady voltage, then it knows that when the current stops flowing, kind of thing, it knows when how to calculate the value. Now, if you hook it up to this one, let me change cameras again. It didn't help much, is it? It's kind of shining on the screen here. Doesn't have a very clear screen, but that's good enough, I guess. I'm going to hook up the same capacitor. Now this one I haven't calibrated, so it might be a little bit out. Well, for some reason it's the 3300. It doesn't like it. It says it's an overload. Yep, I think we've somehow found the limit of this handheld one. That's not very good, is it? It doesn't seem to be able to measure. Where is the I've got this is an old 1000 microfarad capacitor, which is it can measure that. So let's have a look. According to the little one here, it is 1048 microfarads and 0.04 ohms for ESR, which I think, according to the list over here, it is good. It's an old capacitor, but it is still good. But you saw also it's the same thing that came up quickly. But that's kind of disappointing. If it can't even measure a 3300 capacitor. Okay, so let's just want to discharge this there. This one, this meter is telling me that it is 1074 basically microfarads, and its ESR is 0.75, which is different from the other one, but this one is more accurate, so I'd rather believe this one. Okay, so what I've hooked up here is a very small little inductor, which is actually marked to be 100 microhenries, and we are reading let's get to the inductance here. We're reading 99.7 something microhenries, and which I think maybe at a slightly higher voltage, like at 1 volts, we're actually getting a little bit over 100. But let's keep it at the 600 millivolt level. So I've rounded that off to 99.78, and so that's the inductance, and we are currently stuck at 50 kilohertz. That's what I'm measuring it at, because it's a very small inductor. And these are the values that I have recorded. 99 points, I've rounded off to 2 digits, 99.78 microhenries. The phase angle is 83.29 degrees. The reactance is 31.34 ohms. The impedance is 31.56 ohms. And the actual resistive component is 3.69, and therefore if you notate that 3.69 J3134 for the reactance is a rectangular notation, the polar notation would be 31.56 ohms, because that's the impedance, plus the 83.29 degrees. So these values are all available on the display here. So first of all, we got the inductance here. We can ask for the actual resistive component here. That is the 369, which you can see in the rectangular notation there, 369. So that's the RS, S standing for the serial mode, because that is the mode appropriate for that little component from what we discussed before. It's less than 100 ohms reactance, so it should be in serial mode. Then we can actually go over here and ask for the phase angle, which is 83.2823, which is what I have got here on the note, which is part of the polar notation there, 83.29. Then we will also find out that what they're calling ESR, or what the industry calls ESR, this magic value that people always tell you to measure on electrolytic capacitors. And in fact, remember, here is an ESR meter, that's all it does. It just measures the ESR, and then it has a little, it actually tells you, this particular one tells you if it is good for a particular capacitor and so on, so that's kind of handy. There is a little table on it as well. Let me move these out of the way. There's a little table on it as well, which tells you, what the ranges are, but you don't have to look at that because it tells you on the display. So that's kind of interesting, because I don't know if many people realize that ESR value is just in the rectangular notation here, is actually one and the same. See, 3.69, that is also the ESR value of any component, including electrolytic capacitors. You don't really hear much of it being mentioned other than for electrolytics. Okay, so the inductive reactance, and its inductance, because it's positive, see, is 31.34. This D and Q is not relevant right now. Okay, so at 50 kilohertz you can tell that the it is very close to 83.29 degrees, very close to 90 degrees. It's 6.7 degrees lower or something, so there is some resistive component in there, and which is actually the 3.69 ohms. So then if you take a calculator, you can actually verify that this is correct, On this particular calculator, this is how the notation is shown. It's HB28S. It's got 3.69 and 31.34, which is the rectangular notation. And as you can see over here, it has rectangular polar, polar to rectangular. So if we now go rectangular to polar, it has converted it immediately to 31.56, which is now the impedance, and 83.28, which is the phase angle. So that's just how you do that. And when I go back again, it's as simple as hitting that button and we're back to rectangular. So I remember when I was going to college and we had to do these calculations on AC circuits. If I had to multiply or divide them, I would go to polar notation and apply the multiplication or division, because that's easy. And then if I had to add them or subtract them, I would go to rectangular and then add and subtract those. Okay, so I don't know. I hope that was understandable. The polar and rectangular notation in AC circuits actually shows you what how the component behaves. And now, interestingly, there's a frequency component in that. So when I go to frequency and I set it to 1 kilohertz, which is a low frequency for that tiny little component, you now see that the values have changed considerably. That's why you have to know the frequency that these things are supposed to operate on. This is what you get when you at 1 kilohertz. It's still 99.82 microhenries, hasn't changed much. But now you see the phase angle is only 9.866 degrees, because the resistive component has become a lot larger in this equation, because the frequency is lower. So now the inductive reactance is 0.6273 ohms. The impedance is only 3.6582 ohms, and it's mostly made up of resistance rather than inductance, hence the very small phase angle. And the total resistive components is 3.62 ohms. That's actually the resistance of the thing itself. And you can actually verify that if you go to DCR mode here. Now you're going to get the DC resistance. You see, that's purely the DC resistance now, 3.5, 3.6. And what did we get here? 3.6 ohms. Where is it? See, 3.6 ohms is the actual in the rectangular notation. That's the R value there. So the inductance, the reactance is very small, being 0.62, so it's much smaller than the resistor component. So that's kind of how it works. You see, that's when you get a small phase angle, and the impedance is not much larger than the actual resistance of the wire in the coil, basically, because that's what the DCR mode is. And take it out of DCR mode again. So I hope all that makes sense. So and in that case, the polar notation is 3.66 ohm. That's Z impedance, and I've rounded it off, you know. And the angle is 9.87, and that's how it is all put together. So these LCR meters can give you all those values that you can actually work with in calculations for AC circuits. Now, let's discuss a few of those other devices we have here. 1000 microfarad capacitor here. Well, it says 1077 microfarads. I guess that's not bad, but it has an ESR of 0.00, which is not all that accurate. We know it's 0.0 something, but not 00. In any case, it kind of works. This is a cheap thing. Let's put that aside and let us have a look at this thing here, which this is a proper LCR meter. Let me get this set up. I'm just gonna stop the camera for a second. Okay, so this is the DERE LCR meter. First of all, we will calibrate it. Okay, so it's open, so that's currently open. Go. Now these things come with little adapters. This is the one with the two little short leads on it. The big one too, they have an earth socket on there. I'm not 100% sure where I would use that. This one has it too. There is a came with a little lead with a socket that you can plug into this guard socket here, and then you can connect it to one side. I haven't experimented with that, not quite sure exactly when you would use it. Okay, this was pass. Now we're going to go to short, and we're going to calibrate it when it is shorted. Similar to the big one, there's a calibration feature there. Now this thing also came with a TL22. Let me move some of this stuff away, which is a tweezers. Idea is that you can measure SMD components with it, but interestingly enough, these tweezers never calibrate. They always fail. This particular one, none of these buttons work until you take it out of auto mode, which is similar to what the big LCR meter does actually. So now we're out of auto mode. We've got a 214.5 microhenries. We have that's Q, and so again it's similar to the big one there. I can hit this button, that's ESR, and we know that that is the resistive component, and we're currently at 1 kilohertz, so it's 0.19 ohms. Phase angle is that what it is? Yeah, 81.8 degrees. That's all we can pick up from there. This is the resistive component of the device, and remember that is like the rectangular 0.191, and then it also has a DCR mode. The actual DC resistance is 0.18, but I don't know. Oh, it's back in auto mode. This is a nuisance. It's in 1 kilohertz. I don't think it actually tells you the actual impedance, does it? This one. Not in that way. Capacitance, which is... No, it does not. This particular one does not show you the actual impedance. The big one does. So, and you'll also notice that it all has many less digits. You know, there's only one digit here, only 2 digits on the ESR, so it is a lot less accurate. So let's put our, this is the bad capacitor, which is supposed to be 1500. Don't know if that's readable or not. (1500) microfarads at 6.3 volts. For good measure, we'll just touch the two legs. Make sure it's discharged. Okay, so this is the negative side, and this thing does not have a setting for bias for we are wanting to see capacitance. See 271 microfarads, which is way low for that, and minus 20.9 degrees. Anyway, as I said, this is a bad. The ESR 1.54 ohms. That is a high resistance. No good. In fact, this one goes in the bin. One thing I didn't show on the big meter is that it can be used as a milliohm meter as well. And this one too, if you go to, oh, I think it's this button here, isn't it? When you go to DCR mode, it tells you 0.25 ohms, but on the big LCR meter we got 4 digits. It'll say 0.25 da 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 da, which is similar to my milliohm meter, which is 4 digits behind the decimal point. But it is correct nevertheless. These are 4 1 ohm resistors in parallel, so you get 0.255. I think that is an actual fact. This is a I also didn't demonstrate that on the big one, but this is a 30 meg ohm little resistor pack. But again, you see that those crocodile clips are hard. 29.1. You see it's measuring that. And many multimeters have a problem with measuring high ohm, meg ohm resistors, and these things can do it. Now I'm going to take this out and we'll put in the tweezers, which are over here, like so. And we are going to calibrate. Okay, so open, there, open, go. And as you can see, fail. These tweezers have never been able to calibrate. I don't know why that is. they do work, but because they don't calibrate, you wonder if they're accurate. So here I have picked up an SMD capacitor, and it is telling me that it is 14.8 basically microfarads. ESR is 0.1 ohms. ESR is also important for these chip capacitors. They can go bad as well. Finally, let's try my Kelvin clips that I made for this thing. So we go to calibrate, open. Last time I tried it, it passed. No, it says fail as well now. It has passed in the past. So that's the thing with this. I don't know if this one here is actually faulty. I contacted the place I bought them from, and they were nice enough to send me messages, but they couldn't give me any information. They said, oh, that's interesting, but they didn't say if it was supposed to work or not, or whether they could replace it. So it was all a little bit strange. I wonder why before I've had those pass. So needless to say, this is why I wanted to get myself a better LCR meter. It's actually easier to hold chips with these Kelvin clips than it is with those tweezers anyway. 14.73 microfarads. Okay, so this is the MESR-100 device. Its reason for being is to test electrolytic capacitors. It does a quick test. It tells you the ESR, and then it tells you if it is good or bad. This one is that bad capacitor that we know. I threw it in the bin, but I got it back out again for now to test it. And you can see it's got 0.914 ohms ESR, it says, and it would be good if this was less than 200 microfarads, but it's 1500 microfarads, so it's telling me that this capacitor is bad. Here is a 3300 microfarads, and it says good if it is less than 1000 microfarads. So in actual fact, and the leads on it are a little bit corroded, so if I wiggle it a bit, it changes. That's better. 0.177 ohms, good if it is less than 1000, but in actual fact it is what happens if I put it a little bit higher? I don't think it's as corroded over there. Yeah, that's better. You see that the leads are a little bit corroded. That's why it's coming back. 0.087 ohms. Good if it is less than 1000 microfarads. Well, it isn't. It is a 3300. So this one, I wouldn't use this one for a repair situation on a power supply. Here is a little one. It's 35 volt, 470 microfarads, and this one is 0.087. Good if it's less than 1000 microfarads, which it is. It's only half, so therefore this one will be just good. So you can see what this thing is used for, to do a quick scan. I have some very old capacitors. I don't even know how old this one is here, but I think it's been in my box for at least 30 years or more. See, it has quite a high. I would expect that it isn't all that good anymore. So it's saying that this one is not much good either. This one here came out of an old multimeter, which it's about 45 years ago that I bought that thing, so it's also very old. And surprisingly, this one is 470 microfarads, so it says it's good if it's less than 1,000. But surprisingly, this is a Sprague capacitor. I guess it was a good brand, and it's survived all these years. It still appears to be good. And here's another one that came out of there. I should test all those cheap ones I got from China. Maybe they're bad when I already got them. So this one here, it says good cap but low ESR. Well, this is only 220 microfarads, so but it says it's still good. Here is a very large one. This is a new one. 5,600 microfarads at 6.3 volts. I believe this one also to be good. Good cap but low ESR, 0.035. And it's a very big one. Okay, so I think now that's all I've got. That's what it is. So next we're going to be looking at all the devices I have around here for semiconductor testing, transistors and LEDs and all sorts, and see which ones work, which ones don't, and the limitations that they have. So until next time.